好，OK，OK，谢谢。Hello, everyone. Good morning. So let's continue our lecture. 礼拜一的时候我去台大演讲，然后我就站在这里吧，然后这个荧幕大概跟我，然后这个荧幕放在那个地方，所以我大概跟他距离这样，然后我就发现我站太后面了，站在这里太后面，所以我根本看不到，因为这就是，然后我的电脑又离我大概这么近，这么近而已，但我完全看不到你们上面的字。然后，但是我不能动，因为我已经设定录影，所以我就只能站在这里，我不能，这就会超出范围，或者是我移到别的地方去看大荧幕，所以，我就看不到荧幕，然后我想说，哇，我的眼睛怎么变这样，让我非常的难过。哎，来吧，So，哦，然后这个眼镜是新的，因为配了老花眼镜，就啊，人生啊。没想到自己也需要老花眼镜。哎呀，Okay, so let's continue our lecture. So last time we explained how to show the molecular flux. All right, molecular flux is kind of important, kind of core knowledge that um, kinetic in molecular. Uh, Yes, for all the stuff, we will continue. We will frequently use the definition or the result of the molecular flux because this is kind of all about bumping on the wall or escaping the container. All right, because we are talking about the atoms um, striking or through per unit area per unit time. All right. So last time we talked about this, and then we start from one direction, one speed, and write down the equations, and then we found that only few atoms, only few atoms in the right direction to hit the area. So we found that the only few portion should be the question mark. Okay, the ratio should be the question mark. And then we found that the question mark is actually the ratio of this because we found that by using the integration or calculus knowledge that we know that one direction, the ratio between one direction and all direction is actually this value, the blue value, blue highlighted value. All right, and then we can write down this, and then we obtain the result of molecular flux, quarter n under bar v bar. All right, so that's how we did it, and then we straightly use the definition of the flux to define the gas pressure. Okay, gas pressure, also bumping per unit area per unit time, right? And then we do the integration. We found that okay, PV equal to 2/3 average translational kinetic energy. All right, so and then we found that kinetic energy is actually we can approximately estimate the well depth of the potential potential well. All right, so you can see this is really similar to the value we just obtained. All right, and then we talk about the degree of freedom for a molecular. We have translation and rotation and vibration. All right, so let's examine this in more detail today. All right, so that's the quick recap for the last week. Now we are talking about equipartition of energy. Firstly, we talk about translation. Actually, this is just moving around. All right, moving around, changing the position, coordinates in the space. Okay, so we can imagine that there's a particle here, the blue particle. The blue particle has a velocity v. The v, you notice that this is a capital and upright. V is a vector, right? This is a vector. If this Vx, Vy, Vz is a scalar, all right? So if you have three scalar, you combine with together, you can have the vector, all right? So you see the format is different. Please note that, okay? So now the velocity vector v with the component vx, vy, vz. So you can imagine that the v bar square should be mean square speed will be vx square plus vy square plus vz square, and because of the mean, right? So you got you got bar over each component, all right? And this is, so I guess this is the basic vector math, right? So I guess you know that. Then we can have we can further get the conclusion that 1/3 of V2 bar equal to Vx square equal to Vy square equal to Vz square. Why? Maybe maybe some of you may think, this is summed not together, but why it can be separated equally? Equipartition. Why? Because no preference for direction, no preferred direction. Each of them, Vx, Vy, Vz, has equal possibility to choose. Okay, so for the average, they definitely have the same value for each component. All right, so 1/3 for three of them. All right, fair, right? Fair. So the mean kinetic energy per molecular can be written half mv squared bar equal to 3/2 kT. And well, previously we obtained this, right, in the previous pages, and then we noticed that okay, they can be it can be equally distributed to x and y and z. So for each component, x component of the mean kinetic energy per molecular is actually just divided by 3. Okay, divided by 3. So it's half mv squared x bar equal to half kT. So you can imagine that each direction component, each degree of freedom represents half kT. Okay, so yeah, that's it. So you got F equal to 3 degree of freedom in the translation x and y and z, and each of the degree of freedom has the energy half kT. OK， 好，那我们要讲的就是 equipartition of energy。虽然我不知道怎么翻译哈，总之就是其实这个 energy 是有一点就是一格一格一格的，一阶一阶一阶的。好，那 translation 当然就是移动的。那这移动我们可以想象一个 particle， 它有一个速度向量 v， 然后速度向量会有3个 component 嘛，哈 x y z 这个 v 的 component。那这时候我们就来看它的平均的平方速率，平均嘛，因为是平均，好，所以说不管怎么样，你的平均的速率一定是也还是会有三个 component 嘛，一样就是它如果平方的话就是平方，其他的 component 平方加平方加平方和，好，平方和，平方和，好。那接下来呢，我们就会想，其实1/3的 v 平方 bar 其实会等于 vx 平方 vy 平方 vz 平方的 bar。那很特别，为什么它可以直接就是把它1/3切分呢？原因是因为 vx vy vz 它在这个系统里面，我们的 kinetic 的动力学这个假设是它们3个方向都会有一样的几率。那既然是一样的几率，它平均起来绝对会是一样的。然后因为它是很公平的，如果你今天的平均速度 y 比较高，那就表示说，那它比较 prefer y direction， 那这样就不符合假设，所以它们3个会是一样的。那既然之前我们又说1/2mv平方会是3除以2 kt， 是全部的动能的话是2/3 kt， 那我们这边有1/3的话，我们就可以每一个方向的动能就可以写成1/2 kt。那这样就可以发现 x 也是2/2 kt，y 也是 z 也是，那就是有一点，你有 x 方向的话，你就是2/2 kt， 你有 y 方向z 方向加总起来就会是2/3 kt。OK， 好，然后你有3个 degree of freedom， 因为你有 x y z 的方向，自由的动态这样子。Alright, next, equipartition function, equipartition of energy continue, right? So now you don't have you have 3 degree of freedom, but if you are talking about a diatomic molecular, which means that you have 2 atoms in the molecule. Okay, you will introduce more degree of freedom. Let's take a look. For example, previously, if you have two atoms in the molecule, you have basically translation degree of freedom, x, all right, y, okay, and v. So you have 3 directions. You can move as much as you like. So it's a free, right? So degree of freedom, 3 of them. Next, you can have rotational degree of freedom. So you can imagine that this particle, this molecular rotate about x-axis. Okay, so you can imagine that this, kind of, clockwise or counterclockwise, doesn't matter. So you can rotate like this, no problem, right? And you can rotate like z direction. So you can, like this. Okay, so you can imagine this is a molecular, right? You see that, and you can rotate about x, okay, or z. All right, so you have 2 types of rotation. So 2 types. For M5, why we don't have 6, the third one rotation? Because this is a 2-dimensional diatomic molecular, right? So if you rotate along y-axis, okay, I rotate that, but you never see the difference, right? You never see the difference. I rotate that along the y-axis, you never see any difference. So there's no one of the rotation axis degree of freedom is no use. All right, no use. Finally, you have vibrational degree of freedom and also energy. So you can have kinetic and potential energy for the vibration of the diatomic molecular. You see, this spring may have spring faster, or you can compress it and store the potential energy. So you have 2 degrees of freedom, kinetic and potential energy. All right. So in total, for equipartition of energy for diatomic molecular, we have degree of freedom for 7. All right. And then you notice that in the previous page, each degree of freedom has associated with the energy in the quadratic form, which means that it has quadratic power by 2. Okay, power by 2. And the mean value of the energy for a molecular corresponding to each degree of freedom is half kT. We proved that in the previous page. So the total energy of the molecular for this is F kT over 2. So yeah, and the internal energy of the gas should be, we start here. So each degree of freedom has kT over 2, right? So now in the previous page you have single molecular atom, so all the degree of freedom is 3. So you have X and Y and Z, 3. So in that case, each molecular for the single atom gas is 3 kT over 2. Suppose a diatomic molecule should be 7 kT over 2. Suppose, all right. So the total energy of a molecular, one molecular, is F kT squared, kT over 2. The internal energy of a gas means that you have many atoms in the container. So all you need to do is sum them up. Total energy for one molecule, and then you times the total number of the container, and then you can get the total internal energy. So it's half F nkt or nRT. All right, so that's very basic. 好，我们这一页讲的是之前讲是一颗分子，单原子的分子啊，就飞来飞去就是 XYZ 有3个 degree of freedom。现在如果讨论2个molecule， 2个 atom 的 molecule， 那2个 atom 2个原子的分子，组成的分子，那它就会有7个。为什么呢？因为前面3个嘛 XYZ， 然后还有转的方向，一个是朝 X 方向转。朝 Z 方向转，但是为什么不朝 Y 方向转呢？因为 Y 方向转是它自己的轴向，它就会没有看不出来，它转是完全没有状态没有改变的，所以它是没有这样的 degree of freedom。然后还有弹簧 vibration 震动的，它们之间在震动的状态。这震动的状态，我们可以想象它是一个弹簧连在一起，然后压缩的时候它就会储存位能。那震荡，它可以有的时候可以多快或慢嘛，对不对？所以它有 kinetic energy。好，总共7个。那我们说，刚刚前一页证明过了哈，就是一个 degree of freedom 是1/2的 kT 那就是 quadratic form， 就是2次方的一个形式。然后一个 degree of freedom 就是一个1/2 kT， 然后总共那几个你就有几个嘛，乘上 F。那这是一颗的能量。那现在我们要求一整个系统的 internal energy 内能的话，我们就很简单，直接把 N 大写 N 就是全部的颗数的意思，一个 container 一个容器里面全部的颗数乘在一起以后，你就会得到 U 整体的 U internal energy 内能。好，答案是这样。Next, so I just talked about suppose the internal energy or the molecules for diatomic energy should be F 7 times kT, right? But actually it's not that perfect, okay, in the reality. So let's talk about specific heat capacity of ideal gas. So Cv equal to partial U or partial T. So we connected the energy, internal energy to the molecular energy, atom molecular energy, right? So we just substitute F over 2 T, all right? Or we can say F over 2 R. And we notice that Mayer's equation for an ideal gas is Cp equal to Cv plus R. So this is F plus 2 over 2R. Okay, so the ratio between them should be gamma equal to Cp over Cv, F plus 2 over F. Okay, so this is ratio of specific heat, Cp over Cv. Now, we can examine a little bit our monatomic gas, 1-atom gas, all right? F equal to 3, no problem. So 3 plus 3 plus 2 over 3. So this is Cp equal to 5 over 2R and Cv equal to 3 over 2R. Okay, no problem. So gamma equal to 5 over 3 equal to 1.67. All right, so let's see if you have a textbook, we have table 11.1. And you notice that, yes, helium or argon, this type of gas has gamma equal to 1.67, 1.66, 1.67 in the table. They show that. So wow, this is a really good match, right? So the theory is quite good. How about diatomic gas? Diatomic gas should be F equal to 7, right? So F equal to 7, we substitute Cv and also Cp, okay? And we get Cv equal to 7 over 2R, Cp equal to 9 over 2R. Okay, so gamma is a ratio between Cv and Cr, right? A Cp. So you got 1.28. However, for the diatomic gas H2 and O2, this is a typical diatomic gas, right? It is 1.4. So you can see 1.28, 1.4, not really good, right? It doesn't match. It doesn't match. Okay? And a scientist found that, how about us manipulating some number of degree of freedom? If we try 5, we find that gamma equal to 1.4. Interesting. Why they match quite well? Why? So we found that it is not necessarily all the degree of freedom can be used for the standard temperature and pressure. All right. So in the room temperature, actually some degree of freedom are locked. Okay. So we need to see the quantum mechanics distribution is the description is required. Okay. So something that kinetic theory cannot explain this, but in the chapter 15, we can use more difficult theory to explain this. All right， 好，我们前面一页把 U 跟就是 degree of freedom 还有它的1/2 kT 连在一起，对不对？哈，那我们这时候就来写 CV 好了 ，CV 就是那个 U 的微分嘛，哈，那我们就对 T 的微分，然后我们就可以得到 CV 等于 F 除以 2R。那如果使用 Mager log 的话，就可以得到 CP 是多少？那它们两个的比值就是伽马，对不对？哈，好，那时候我们就来试试看，如果我们用一个原子的气体，我们就发现算发现，哎，伽马会等于 1.67。那我们看课本的表11.1，我们就发现他们提供的 helium 和 argon 这两个气体，哎，它真的是伽马就是这样数字，所以表现得非常好，理论做得很好，就是可以 well matched， 可以很合。但是如果是 diatomic gas 的话呢，我们带7进去，就发现根本跟有名的 H2 跟 O2 都不合啊，对不对？哈，伽马就是很奇怪，实验跟理论没有对上。结果科学家发现，不要带7，带5反而就对得很好。 那这代表一件事情，就是其实在一般的状态下，某一些 degree of freedom 是被锁住的啊，即使有 degree of freedom，但是它还没有被激发出来。那这表示说，我们的 kinetic theory 动力学没有办法完全的解释这件事情，我们必须要等到第15章用 quantum mechanics 量子力学来帮忙我们解释这件事。OK， so now distribution of molecular speed. Remember, we have a F, right? We have a normal distribution F. And we say, oh, the F is the distribution of the speed, right? But what exactly it is, okay? We don't know the distribution is. So now we are going to determine that, okay? So distribution of molecular speed is actually what we're going to get. The purpose of this page is possibility, density function, F V. So as I mentioned in the previous few page, we always say, our V is looks like this, and this is FV, right? This is V, okay? So what on earth is this? And now we are going to determine that, all right? So the particle with the velocity V, of course, the V is a vector, okay, a vector. And the later, the italic V is the magnitude of the velocity, okay? Now, we can write down their relationship. Okay, the velocity vector with absolute value is, okay, the scalar magnitude of the velocity, italic V, okay? Okay, so later we will use this to do some Maxwell-Boltzmann distribution, okay, in chapter 14. So we will use that later. So this is quite important, all right? So now I would like to introduce several difference between something coming up later, okay? FV we learned that, right? FV is a distribution. And the V here, they are all italic, right? So italic means that only for value, magnitude, all right? So the fraction number of the molecules in the speed range of V2, V plus dV, irrespective of direction, because it's all value. So this is not vector, so no direction. Okay, so this is only value because it's italic. All right, and remember this is a fractional number. Okay, now we want to do something. We want to invent, introduce a new stuff, new thing. But all you know, you can see that they are related. They are very similar. They can be transferred by some equation or function. All right. So now, because this is a little bit difficult for doing something for the next slides. So we introduce something really similar to it, and then it's perfect for our starting point. Okay. So now we introduce something similar but different. Okay, so this is capital F. This is not small letter f, okay? And this f is actually the number of molecular, not fractional number, not the ratio. This is the actual number, okay? And you notice that this is capital V, so it does relate to direction, okay? So nothing here, okay? So it does relate to direction, all right? And with the direction from here to here with the value changed, okay? So we will use this. It's easier for us. And then we can, once we found the relationship of this, and then we can refer back to this one. All right. 好，我们接下来要讲这个其实蛮重要的。我们之前不是都说啊，这个一个 container 里面有的速率是 normal distribution， 应该说类似的哈，几乎是 normal， 应该说我不知道是什么 distribution 了哈，但是它一定是长这样的。那这样子到底是什么？那我们不知道 ，OK？ 那这时候我们就要把它算出来啦，哈。那今天要算这个 distribution of molecular speed， 就是在算这个 FV， 好 ，FV 这个小 f 小 f 斜体 v 啊，我们想要算这个。好，那要算这个东西，那先介绍一下 FV 就是这个小 FV， 小 f 就是 fractional number 是比例哦，是比例哦。那 v 的话是只有数值而已，数值，所以它跟方向是没有关系的，好，是没有关系的，也就是它不带方向。如果你要考虑所有的方向，你要去积分它哦，但是如果今天是用这个的话，对我们来讲，接下来的推导会比较难，所以我们就做了一个介绍一个比较有关系的大写 F。然后向量 v 这样子的东西，这样等一下会比较好解释。但是他们其实你可以发现，他们其实非常非常相关的。好，你如果求出这个的格式，其实这个格式应该不会差到哪里去。OK， 那一个是 fractional number， 一个是 number。好，那当然了，你可以知道，反正 fractional number 跟 number 其实也很快啊，就除个全部的就好了。那接下来是速度，它上面是速度，它这边是向量的速度。所以它有考虑到所有的 direction。好，那这边就等一下就会使用它，但是这两个东西一定是很相关的，它们会有几乎一样的 format。OK， 等一下就会用到了。So now let's take a look. It's called Maxwell-Boltzmann velocity distribution. Okay, so now we use this capital F vector V. So in a dilute gas, we assume binary collision and conservation of momentum. Okay, so kinetic theory scientists always assume a simple way or simple way or general way to do the math. Okay, you can see this two particles bump to each other. We are not talking about three of them because the bumping is too quick. You never find exactly the same bumping with a 3. Okay, so this is an assumption. All right, so we only have binary collision. And then you always can find this type. Okay, V1 as a input velocity. For V2, the second particle, V2 input velocity, and output V1 prime, V2 prime. Okay, so this is a type of the one possible collision type. Okay, and we can notice that the number of collision occurred between molecular 1 and 2 per unit time is actually the FV1 and FV2. Why? Because this is a chance, right? There's a chance here, and this is the chance here. So if they want to bump together, they meet each other. So you need to time. The possibility should be timed together. right? FV1, FV2 times together means that both of them using V1 and V2 bumped at this moment. The probability or the number, oh sorry, this is not probability. Very similar to the probability, but this is a number. The number of collision in this container should be FV1 times FV2. Okay, so now, of course, there will be A is a constant of proportionality. What does that mean? Constant of proportionality. What does that mean? It means that if you have greater container, bigger container, your A is bigger. Okay, and if you have a smaller container, which means there's a scale. Okay, scaling factor A for bigger container, A greater. A smaller means smaller container. Okay, and then interestingly, you can always find a mirror. Okay, mirroring case for this by V1 1 as an input, V2 1 as an input, and bounce back to V1 and V2. Okay, so you can see these two things, two cases, but the inverse correlation is a mirror. Okay, just like mirror, you see the mirror and you see both of them. And the right hand side will be V1 plot and V2 plot FF. Okay, and of course the alpha is the same because now we are talking about the same container. Okay, so they deleted other, and we notice that because they are mirroring, so their number should be the same. So FV1 FV2 equal to FV1 plus FV2 plus. Okay, so now if you can accept this, we found that they are times together, right? So we do the natural log to make it split, become plus. So natural log of FV1 plus natural log FV2 equal to natural log FV1 plus natural log FV2 plus. Okay, they are the same. So we can say this is equation 1. Okay. Then the constraint. What is constraint? Constraint is for the conservation of kinetic energy, right? What is conservation of kinetic energy? Half mv squared, right? For the kinetic energy for each atom, half mv squared should be its own kinetic energy. So for the particle 1, V1 plus V1 squared plus V2 squared. So the input kinetic energy, input kinetic energy need to be equal to output kinetic energy, V1 plus squared plus V2 plus squared. But maybe you will say, why there's no half and half and half and yeah, because they cancel each other. All right. So conservation of kinetic energy is that no energy loss for each bumping. So you need to obey this V1 squared plus V2 squared equal to V1 plus squared plus V2 plus squared. Okay, so this is the constraint. You need to satisfy. You definitely need to satisfy that. And then we will later use this as a second equation. So it can help us to solve the problem, solve the F. Okay, but here conservation of kinetic energy is using the scalar, right? But don't worry, because v dot v is a vector dot, right, equal to v square absolute value equal to v squared. All right, so you know v dot v equal to this. So then we can transform by using this and that, we can transform a constraint here in the vector form. So it should be v1 dot v1 plus v2 dot v2. You can see that what I'm writing is vector form. Okay, this is really difficult. So how about just all right, equal. So this is plum. Okay, that's it. So the constraint from the conservation of kinetic energy goes up, become this. So we have equation 1, equation 2. So by comparing equation 1 and 2, we know that actually F V looks like what? Only one type of function can satisfy two equations simultaneously at the same time. You can see that natural log function plus them together will equal to each other, and the v1 dot v1 plus v2 dot v2 equal to this. Only one of them, only one form of the function can satisfy this. Let's take a look. If the f should be looks like exponential v dot v. So now you can take a look. If the f looks like this, yes, if you do the natural log, it becomes v dot v, right? So v dot v, do the natural log, it becomes equation 2, okay? So it simultaneously satisfies both of them, both of the equation. So yes, fv looks like exponential v dot v. But how can we write that? Write down fv equal to exponential v dot v. Okay, it looks like this, but still we need some coefficient. The first one is a, because as we mentioned, we have the constant of proportionality. So which means that if you have greater container, you will have greater A, okay, something like that. And also the v dot v also needs a constant. I don't know what constant it is, but we will examine that later. Okay, and then the alpha can be positive or negative, but because later we know that it will be negative. So how about we just give the negative sign here? But it doesn't matter. Okay, it's just a symbol, and then we can prove that later. 为什么它不让我 ？Okay. Now, so this is F. Capital F looks like. How about let's write down small f. they must be really similar, really similar. It becomes a plan exponential minus alpha plan v squared. Okay, so that's it. OK， 好，最后1分钟，我们就要把它，我们要找出来嘛。我们刚刚写的 F 嘛，对不对？好，大写 F。那这时候我们就说，我们在一个 container 里面，我们假设它只有两个两个颗粒的碰撞，不会有3个，因为它们太快了，撞完以后就走了，撞完以后就走了，所以不会有3个同时，没有那么强。好，那而且它会完全的能量守恒。好，那这时候我们就假设一个 V1 入射 ，V2 入射，然后离开的时候是 V1 plan 出射，一个是 V2 plan 出射。好，那这个就可以说，我们这个东西是需要2个同时在一起，对不对？哈，它的几率是要同时在一起的，所以它是要相乘的哈。那到底有几种这样的状况呢？就是 FV1 跟 FV2 乘在一起。那这个 A 它是一个大小的常数，哦，这个常数它如果今天容器很大，它的 A 就要变大；容器很小 ，A 就变小。OK， 好，那跟个数有关嘛，哈。好，然后接下来我们做完这个以后呢，我们发现一定会找到一个跟它镜像的状态，就是 V1 plan 入射 ，V2 plan 入射 ，V1 V2 出射。那所以说它会写成这样子。那这2个一定是一样的一样的个数嘛，哈，所以要相等。当然这个阿尔法A 跟 A plan 这2个东西是一起的。那同样一个容器，所以把它消掉了。好，那这个东西写成2个相乘等于2个相乘，我们想把它加起来，比较好算，所以我们就用做 natural log 把它做成相加的状态，就是第一个式子。但是这个东西需要符合一个要求，就是能量守恒。能量一颗的动能就是1/2 mv 平方。那我们就是 V1 V2 V1 plan V2 plan 的速度，它的动能都要是守恒的，所以入射的动能要等于出射的动能。那当然1/2 m 已经被消掉了，所以才会长成这样子。那这个要怎么把它跟上面这个 vector 一起写呢？我们就会发现，其实 V 打 V 向量内积就会是 V 平方，所以我们就把这个东西写成 vector form， 就变成向量的形式，就会有第一题跟第一个式子跟第二个式子。那这2个要同时结合在一起，才可以把 V1 V2 解出来，F 解出来。好，那这时候我们就来仔细看一下，这样子的长相要同时满足这2个式子，只有一种可能长成这样子，就是 exponential V 打 V 这样子的式子。F 这个函式才可以同时满足这2个式子。OK， 然后我们就写成这样。但是呢，因为这边是等号嘛，所以说它的系数都会被消掉。那这个东西就要把它加上去，不然的话就真的这样。如果你直接把它设成1的话，真的不对了哈，因为它有等号，等号的话，它的这个系数都会消掉，那就会写成这样子的式子。那这当然这个负阿尔法其实它也是一个常数，但是为什么要写负阿尔法？你要写阿尔法跟负阿尔法其实是一样的哈，但是之后就发现它会是负的，好，所以说我们就直接写负阿尔法就好啦。那等于这个其实没什么关系哈，你写阿尔法跟负阿尔法都一样，它只是一个它只是一个符号而已。那只是等一下之后要变成负的，会写成负的会比较好讲解这样，好，之后就会变这样。那这个 F 是capital 的，那其实它们2个都是有一样的形式啊，只是不同的一个是否向量，一个是否数值，那就把它写成这样子。OK， 那等一下我们就会继续用到。好，对不起，我让大家迟了3分钟。我们 I will see you after 20 minutes, so it should be 13 past 10. All right, thank you.
嗯。发票，什么意思？我不怎么会帮我放这么奇怪的东西吗？因为上次整理的时候很懒。
Okay, welcome back. 好，加油加油加油！不知道为什么今天就好累哦，应该说每天都很累，怎么会这样呢？唉，既然很累，来聊什么事呢？怎么办？好像也没什么发生什么事。那生活好像过得有点无聊，那我想想看，有什么事情可以分享？哦，我们上次不是聊到那个我在讲那个动物啊，然后速度很快啊，然后就是寿命比较短啊，然后就有同学不知道是同学还是谁啊，但应该有看那么仔细，应该是同学，他在下面留言，不知道大家有没有看到？他说猎豹跟狗，猎豹的速度非常的快，但它们的寿命差不多。哦，好认真呢。那但我自己在想，我那时候讲的不是速度快不快，我讲的是它的反应，也就是说，猎豹跑得很快是因为它肌肉很大，不是因为它反应很快。但是狗，它跟狗跟猎豹可能反应差不多，只是狗没有肌肉那么大，所以它们寿命差不多。不过没关系啦，搞不好他等下这位同学，等下下来之后看到这一次的，就会跟我回复我很期待啊，我很期待跟大家聊聊这件事情啊。好，不过前几天我又发现，好像动物的寿命跟体积不对啊。我前几天看到，不知道在哪个网上跟体积有关，这不对啊。大象寿命也没有乌龟长嘛。不懂啊，算了，反正就是最近看到，哎，我的 YouTube 竟然有人看，然后下面还会有留言，我很开心，叫做粉丝互动啊，太棒了啊！对，然后哎，大家应该知道我明年要离开这个系了吗？啊，有人惊讶，所以有人不知道，大家知道吗？知道吗？不知道，不知道哦。谢谢各位的照顾，谢谢这个系的照顾。对，那对要转换跑道了。那我觉得我这个年纪应该也算是蛮刚好的啦，哈，就是我在这边12年，然后很开心，那有这个机会，想说12年也做的差不多了，那就来换下一个跑道吧，下一个工作。所以说，其实这一次我应该算是我不知道之后还会不会回来学术界啊，但是我是说，可能近年来这将会是我最后一次教课，这样教固态热力学。然后，而且我也觉得我很好笑，明明就是最后一次最后一学期，我还在改我的计算机概论的教材，我真的是神经病，我干嘛把自己搞成这样呢？以前以前的教材就是比较吸引同学来写程式这样的，但是后来发现 其实蛮有趣的，就是后来发现着重在有趣，然后下一个进阶课程叫做什么材料跟机器学习嘛，哈，就是由国家高速网络计算中心的研究员开的。但是他们发现，就是如果今天着重在有趣的游戏的设计，那在后面的深的课程就比较难衔接，就可能这个不会，那个不会这样。那所以为了要好好的衔接，所以我就想说，好，我一定要，我要做一些调整，我要把它调整，就是说这一次的计算机概论是上完我的计算机概论，你就可以学会如何做数字辨识的 AI 这样。那我的目标就是这样，也就是说，就是那种一般这是什么车牌辨识那种，然后都可以做到这样。好，结果我就为了这样，我就改了。这学期我就是全新的教材，然后就一直跟 ChatGPT 合作啊，然后就改好。然后每个礼拜的投影片，我都是上课前3分钟才把它做好上传，这样把我自己搞死。结果很好笑的事情是，我要离开了嘛，结果那几位国家高速网络计算中心的博士研究员就说：“哎，那你离开了，那我开了干嘛？”然后他就不开了，所以就是好像我的离开好像有点牵扯到其他事情这样，然后就离开了这样，然后就没有这课，所以我没有那门课要开，那我为什么要为了那门课改我的原本的计算机概论的课呢？所以整个就是很非常的非常的傻啊，弄完自己的累。对，我已经有大概，我目前已经做到第五章节，然后我每一次的投影片都是前3分钟、前5分钟才上传，然后做的都很就是很紧急这样。那当然自己也是有问题的哈，就是时间控管也有问题。不过跟大家分享，就是 ChatGPT 真的是一个太厉害的东西了。好，就应该说 AI 啦哈，大型语言模型真的是太厉害的东西了。他们对城市的理解度实在是太厉害了。好，那我有一个想法，就是它其实是你可以把它想象成一个是别的国家的实习生或是助教这样子。他就是别的国家的人，他是人，AI 啊 AI 啊，他是来自云端好了，他的国家叫 Cloud 好不好？然后他来到我们这边来帮助我们，然后他一开始是只会看得懂程式语言，他的第一 native language 就是程式语言，所以他程式语言写的超棒啊，所以你跟他沟通，如果你写程式，他一定听得懂我们在讲什么。但是现在他学会了新的语言，以前只会听得懂程式语言，现在他学会了我们这些人的语言，我们真人的语言。那所以，我们叫他把我们的想法写成程式的话，他几乎100%都会，除非你讲的不好，他大部分都会完全按照你讲的话把它完整的写出来程式语言。所以其实计算机概论如果不用 ChatGPT 的话，我觉得那位老师就太可惜了啊，太可惜了，因为真的太强了。随便叫他给我一个例题，哇，他可以给一个非常非常好的例题，然后叫他解释什么程式员的函式，哦，全部也解释的非常非常好。当然一定会比这个固态热力学还要好，而且不用加任何的呃讲义啊或什么之类，他就已经做得很好。所以我真的觉得，如果你想要学程式的话，现在是最好的时机，因为 AI 就可以就是一个就是像是一个家教一样，你就问他，他就会回答你了。哦，所以其实现在已经不需要老师来教计算机概论，说实在的。好，那另外一方面，也就是我们已经没有借口了。哇，我觉得其实现在这个科技发达哈，资讯爆炸这个时代，我觉得大家都会过得越来越辛苦。为什么？就是 好像会变得比较轻松，但是实际上会变得比较辛苦。为什么？因为我们已经没有借口了。就像是我们现在有的时候常常会问一些问题，一定会被人家说你 Google 就有了。但是以前的人没有 Google，你就问问题，那别人就会好心回答你。但是现在就因为有 Google 这件事情或者 AI 这件事情，它就会，哎，好像你本来就该知道一样。那这样的话就变成人类就会有好紧张啊，我是不是少知道了些什么这样？所以这其实是蛮紧张的，这是蛮现代人的悲哀啦哈。不过也是啦，都有各个年代都有各个年代的好处啦哈。好，Anyway，let's continue. All right, so we just talk about how we determine the form of the function f. It should be looks like constant times exponential with the power of certain formats with velocity with square. All right, so let's continue. The Maxwell speed distribution. So now let's try to get the alpha and a. All right, so let's take a look. The MVdV is the number of molecules in the speed range of v to v plus dv, and because this is a scalar v, so it is irrespective to direction. Okay, so MVdV must MVdV. Okay, so sum of the because this is no direction, right? So we need to times the surface area, the all direction, so surface area of the speed sphere. Okay, and you see the number of molecular in the speed range. The number of molecule is the velocity in the range. Okay, so this is basically we're talking about the same thing. All right, number, but this is irrespective of direction. So we need to times the surface area of the speed sphere. Okay, so 4 pi v squared and fv dv. So it will look like this. So mv should be 4 pi v squared times fv. All right. Now we know that the fv equal to looks like a times exponential minus alpha v. Okay. So we can return mv dv equal to 4 pi v squared a exponential minus alpha v squared dv. Right. So this is mv dv. Okay. So the number of molecules in the speed range be written down like this. That's connecting to the energy. Energy, the container is 3/2 nkt, no problem. But we need to find, we need to sum them up from the right hand side. Half mv squared, right? Half mv squared. But we need to times all the number. So you need to do and all the number within all the range of the speed, right? So we need to do half mv, half mv squared, but we need to do the integration to from 0 to infinity velocity, mv dv. So when we sum them together, it will equal to the 3/2 nkt. Now, this is the equation that we are going to solve, right? And next, we can make the n to the right hand side. Okay, and also n go to the left hand side. All right, and half. Okay, delete it. So you got 3kt over m at the left hand side and equal to something remaining n go to the left hand side, right? So integration v squared n v dv. Okay, but this is n, right? This is n. But can we make it in the form like the above? Can we do that? Yes, we could do that. Because this is the number. If we do the integration 0 to the infinity, we do the integration nv dv itself, which means that we sum them up all the number, because you can imagine that this is just times 1. Okay, so you just count all the velocity number, right? Count the number of all the velocity. So actually, this is n. Okay. So I will give you n. Okay, this is n, the number. Now we have a really ugly form. 4 pi a 0 to infinity v4 e exponential minus alpha v squared dv. Four pi a 0 to infinity v squared exponential minus alpha v squared dv. Okay, so now very difficult, right? Very difficult to do the integration. Luckily, we have the help from smart mathematician, and all the mathematic tool is listed in appendix D, equation D.2. It told us 0 to the infinity x 2n exponential minus ax squared dx equal to 1, 3, 5, 2n minus 1, 2.2n an pi a square root. So this is actually the legacy of the smart mathematician, mathematician. Yeah, they found that if you have this form of integration, it actually looks like this, and this is the n. So we found that, oh, this n here is n equal to 2. This is n equal to 1. So we can break 2 times 4 times alpha square pi alpha half. Okay, and 1 over 2 times 2 times alpha pi alpha half. Okay, that's it. Then it becomes 3kt divided by m equal to 3/2 alpha. Okay? So alpha equal to m/2 kt. Good. Okay. And if we substitute this to the above equation, we can further get A equal to alpha pi 3/2 n equal to m/2 pi k kt 3/2 n. Okay. Wow, ugly. All right, so we can substitute back A equal to an alpha, right? And we can obtain such ugly term. All right, so MV dV become 4 pi n, blah, 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 blah. So ugly, right? So you can see that if you have a velocity in the x direction, y is mv. So you can see that is a v is, if you specify the velocity, you can get the exact number of the atom with that velocity. Okay, so you can find that this equation, if we using Excel, we input different v, it will give you a distribution. Of course, there's a t as a parameters. So if you have t changing like from higher temperature to lower temperature, this distribution become here or here or here. Okay, so you can see if you have a higher temperature, you can induce higher speed. Okay, so you sort of flatten this distribution. But if you have low temperature, most of the number of molecular is with the lower velocity. OK， 好，终于讲完了，超复杂的啊。总之呢，我们前面不是有说 FV 是这样子的形式吗？前面已经算出来了。那这 FV 还记得吗？它叫做在这样子速度的范围里面有几颗分子嘛？哈，那这不就是这个吗？在某个范围里面有几颗分子？可是问题是现在刚刚那个是有速率的嘛？现在应该说有向量的速率，有方向的，但是这个 NV 是全方位的，所以你必须要乘上4v 平方，考虑所有的方位，然后乘上就是有指派的那个单一的 vector 的 FV 以后，然后乘上 dV 就会变成 NV dV。OK， 好，那这时候我们就把这写上去啦，写成这样子。那这时候这是某一个速度范围之间的颗数。那现在我们把这个颗数乘上它自己的1/2 mv 平方的话，那全部加总起来积分起来就会是3×2 nkt。好，那这时候就是1/2 m 做积分，好，做积分从速率为0到速率为无穷大。好，我们就做这个积分。那这两个式子会相等嘛？哈，那我们就把 n 移过去，把 n 移过来，然后1/2除掉等等的，也就是得到左边是这样子，右边是这样。那这边值得注意的是，下面这个 n 变成这个样子的，这什么意思呢？还记得这个 NV 的定义是什么吗？是 在这个速度范围里面的个数啊。那如果今天我从0积到无穷大，啊，不就是全部的个数了吗？好，所以这边是 n， 我写成这样子。好，那这个式子代入进去，发现哇，好丑哦，这好丑，根本就解不出来嘛。没有，其实数学家已经解出来了，他找到了一个公式，写在 Appendix D 里面，然后我们就把它顺利的解出来了，感谢数学家。然后做完以后就得到这个式子，然后我们就发现哦，阿尔法等于这个东西，带回去以后，我们就可以把 a 解出来啦哈。当然这边要有 n 的哈，要把它解，就是啊，不对，不是，讲错了。我们要带哪个公式呢？我要带这个公式。哦，这个是这个阿尔法带进去以后，这个东西等于 n， 哦，就可以解出来了，哦，就可以解出来了。或者是甚至你可以说这样好了。Sorry, I didn't say very clearly. How about we substitute this? How about we substitute this part? And which is equal to n. All right, and then you can solve the a. All right， 好，那 a 就变成这样子，好丑，好丑，把它带回去这里公式，好，得到这么长的丑丑的东西。好，这时候如果我们用 Excel， 我们就可以把它画出来的哈，用不同的 t 改变不同 t， 它的那个 distribution 就会长得不一样。那这边的意义就是说，温度很高的话，它就会有更多的高速的原子出现，但是如果温度很低的话，大部分都是低的速率的 particle 的颗粒。那我们终于把这个速度的 distribution 都找出来了。好 ，all right, so now we have the exact form of NVDV. Okay, so then and also we know the information of alpha and A. So we can start to go back to where we were. Okay, here, this is where we were, right? We say mean speed, rooming square speed, and most probable speed, blah, 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 blah. Okay, we now can literally count, determine those values. So now this is MVDV, right? MVDV, we just done that. So MVDV is respective to direction, which is very similar to FVDV, right? So all we need to do is FV equal to NV divided by N. That's the fractional number. Remember that? Remember this? Okay. Remember this? We wrote it here, right? All right. So, sorry, let's go back. Okay, MV. Now, so we just substitute that. Okay, so we can get this one. And so this is mean speed. Remember how we get mean speed? Expected value. So V times FV dV, and do the integration from 0 to infinity. So this is a value. I know it will be difficult, but if we just using appendix D2 and D3, 2, D3, we will get the result. In the mean speed should be looks like 8 pi. All right, and the rooming square speed should be 3 square root, and Vm, the most probable, is square root 2. All right, so let's take a look. If we say the Vm Vn is 1, all right? Because it's at the center, right? At the center. Vn is 1. And the root mean square speed should be 1.225 times of Vn. And this is 1.128 times of Vn. So actually, Vn, V bar, and V bar square half. Okay? So this is really interesting that V bar mean speed is not the most probable speed. So this is not average speed. No. The mean speed is a little bit greater, 1.225 times of the most probable speed. Interesting. 好，我们终于可以拿来用了哈。我们的 NV 底 V 是在速度的区间有几颗？那我们的 FV 还记得吗？它就是 the fractional number 的比例啦，哈，比例在这个速度之间的比例，占的比例的颗数是多少 ？OK， 颗数占的比例是多少？所以要除以整体的 n。好啦，那这时候我们就可以把这个之前我们都只是写出 FV， 好，我们终于可以把它带入进去了。当然前面的很丑的事就要带入进去，然后做积分很恐怖啊，没关系，我们就借助 Appendix D 的做法，我们就可以得到这几个数字 ：mean speed 跟 root mean square speed，平均速度跟均方根速度跟最高几率速度。OK， 结果我们就发现，如果我们拿最高几率速度来当做是1的话，1单位的话，其实均方根速度会是它的 1.225 倍。然后它的平均速度会是它的 1.128 倍 ，OK？ 我刚刚是不是讲错了？总之1.128倍。那我们就会发现，如果真的这样把它画出来的话，最高几率的是 Vn 吧，哈。但是 V bar 平均速率竟然还比这个最高点高一点点哦，还蛮特别的吧？其实也不会特别啦，哈。我们用想的也知道啊，为什么？因为这边到0就结束了，这边有无穷大。无穷大终究都会把这边的东西往右边推一点点哈，所以其实也蛮合理的哈。然后接下来 V 就是均方根，它是是不是最大的 1.225？OK， 好，大概是这样。Right, next one. It's very difficult. All right, this page is a little bit difficult, and textbook only have several texts, several sentences. And then just say, this is the result. Bye. Okay. So this is very, I don't know the textbook why, I don't know why the textbook just provide such limited information for us. I don't know why. So yeah, this information has been asked by your seniors many times. So I decide to write it down and I introduce to you. All right. So speed distribution in one direction only, one direction. Okay. So previously we talked about 3 degree of freedom, X, Y, Z, right? So it is a sphere, speed sphere. Okay. 3 degree of freedom become NV dV 4 pi v blah, 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 and the answer is this. We just done this, right? We just know how we get this in the previous few pages. But for one direction only, 1 degree of freedom, for example, NVX dVX, what will it be? Okay, why we learn this? Because it is useful in chapter 14.6, all right? Because the equipartition of energy, okay? Previously, we talked about the equipartition, X, Y, and Z. They will have exactly the same kind of energy spacing, energy level, okay? But now we only get the 3 degree of freedom. We only prove the 3 degree of freedom become that very ugly. How can we get the NVX dVX? And in the textbook, it just said, oh, the answer is this, and never explain why, okay? So now I will lead you to step to get that result. All right, so here, F Vx dVx. No problem, right? Previously, we do this and times the sphere area, but now we only have one direction, so no problem. We don't need to times anything. We don't need to times anything because it's one direction. All right. Now because they have all the directions, so you need to have 4 pi v squared. But here, one direction, no problem. Okay, so now it will become AE minus alpha Vx squared dVx. Okay. Right, so you can compare a little bit like here and here. This is 4 pi v squared. And this one. So there's nothing here. Everything become Vx, Vx. Okay? That's the thing. And then I draw a figure like this. Why? Because you can see that if the V is changing, in the 3 degree of freedom, it's all direction, right? So it should be regarded as a ball growing up and growing down, shrink and ball growth, okay? But now in one direction means that the velocity is only has x, for example, x direction, okay? All the velocity is actually a plane moving. If you increase the velocity, it's actually move this the plane forward. If you decrease the velocity, you move the plane backward. Okay, so the growth direction is different from 3 degree of freedom or 1 degree of freedom. 3 degree of freedom is ball growing, and 1 degree of freedom is plane moving. Okay, this is the main difference between the two. All right, and I will give you more detail in the next slides. 好，接下来我要讲的是这个刚刚讲到的 NV dV 会长这么丑，对不对？哈，那它是 3 degree of freedom 3个自由度，也就是 x、y、z 都一起考虑进去，对不对？哈，但是这个东西我们当然算出来很棒，但是之后我们在第14章的时候，我们会需要一个东西叫做 equipartition， 也就是说刚刚讲到了 degree of freedom 要分开看，因为它们每一个都有自己的能量能阶嘛，哈，我们要把它就是分得清清楚楚的。所以呢，刚刚那个3个的是混在一起的，不好用。我们现在要写的是一个的，也就是 Vx、Vy 或 Vz 这样子。好，可是课本上哈，就是提供非常非常少的资讯，就是直接跟你说答案就是这样，然后谢谢大家，然后就继续下去了。然后所有的学长姐都看不懂在干嘛。好，那包括我一开始我也看不懂在干嘛。后来我被问了很多次了，所以我就好好的把这个东西解出来，然后放在这边教给大家。好，那就这样开始哦。就是大家刚刚就知道，就是说3个方向的速度都应该不是3个方向，各个方向的速度都要被考虑到的话，它速度如果变大，是这个球整个被胀开或变大，或是整个球缩小速度变慢的话，就被缩小，对不对哈？这是 speedball 嘛，对不对哈？那现在右边这个是什么呢？因为它只有一个方向。所以说你的速度变大的话，就是一个整个 plane 一个平面往前走，往正的方向走。那如果是速度降低，就往后走。所以实际上这个 v dvx 的改变，它其实是前进跟后退，是一个 plane 的前进跟后退。 好，然后另外一件事情是这个 3 degree freedom，NV dV 跟 NVX dVx 有什么差别呢？因为它别忘了这边有一个球的面积，但是没有啊，它就是一个方向啊，所以不用考虑其他方向 ，FVX 就已经够了。好，那接下来所以我们就会发现这边跟这边的差距就是差在4V 平方，然后等一下还会有个差距就是增进变化的方向。Okay, next. So now left hand side is for V and the other is for Vx. 3 degree of freedom, right? And this is 1 degree of freedom. Now, we just done the explanation in the previous page, no problem. And total number, the same, n equal to 0 to infinity, mv dv. Now, this is because you are talking about the ball growing, right? So your origin is 0 to infinity. But if you are talking about one direction plane moving, your integration is minus infinity to infinity, because you are thinking, yeah, here you see your plane can move along x in minus infinity to infinity. All right, so this is so important. The main difference between the two, okay? And none of this mentioned in textbook, okay? Then total energy, 3 degree of freedom. And this is the 1 degree of freedom. All right, so 1 degree of freedom become half NKT, and 3 degree of freedom become 3/2 NKT. Again, from minus for Vx, for 0, from 0 for V. So basically, we are considering a ball growing, right? And this is considered a plane moving. So they are different, okay? Then left hand side, we have done that. And this is for appendix D1, appendix D2. Okay, and this is, we've done this. So I won't explain the left hand side because we've done that. The right hand side, we do this KT over M, and then the using the appendix D, D.1, D.2 to solve this. And alpha is still equal to M over 2 KT, but the A is a little bit different. It's 3/2 half NK, half. So combined together, we notice that there's no 4 pi. Okay, and here's 3, is 1. And that's it. That's it. OK， 好，我们要讲的就是刚刚我们已经讨论过3个方向的，也就是应该说各个方向的，它是球的增长，从0到球，速率为0到速率为无穷大，它是一个球这样长来长去。但是如果是 Vx 的话，它可以平面在移动，它可以到负的无穷大到正的无穷大，所以这边是最大的差别哦，就是它的积分是一个从0到无穷大，一个是负无穷大到正无穷大。那接下来还有另外一个差别就是3 degree of freedom， 它就是3除以2 NKT 嘛，哈，那这边是1/2 NKT， 因为它只有1个 degree of freedom。好，然后一样，这边是从负无穷大到积分到正无穷大。那接下来就做这个积分嘛，那要靠的是 D.1 跟 D.2 的方程式，然后算出来 alpha 跟 A 都差不多，只是差在3/2跟1/2。那全部算出来以后呢，左边右边可以比较看看哦，只差在一个系数， 跟这个3不见了，就这样。All right，右边这个东西会在第14章用到。好，3分钟，跟大家聊聊，就是为什么要离开哦？就离开这里，就是这里很棒哦，我觉得过得很开心，而且我才刚升上特聘教授，那我才刚上特聘教授，所以我才正要开始爽，对不对？但是为什么要为什么要这样呢？就是你看，就跟刚刚那个计算机概论改教材是类似的，就会把自己搞得很累这样。那后来发现就是好像那间公司是需要我的背景啊，就是我要做我之前做的东西就是材料模拟跟 AI 嘛，那正好这3个是被那间公司需要的啊，所以说他就来问问看有没有机会去那边做研究这样。那我觉得还不错，那我就觉得，如果今天是去做别的事情，那我可能就不会想要去。但是这正好是我之前在做的，也是我的兴趣，所以我就想说，好，那可以试试看，换一下跑道。然后我从来没有出过社会，我以前也想要知道说，我工作的经验，当然我会觉得自己做的 OK 嘛，就是12年，然后现在特聘教授，我觉得做的也很好，然后上课也算是开心，然后也有得到一些奖项、一些肯定，我觉得那这样子的我到社会去会被碾压吗？我也不确定，那我们就来试试看这样。那现在已经40几岁了，在早5年也不太对嘛，早5年就不适合，因为太年轻没办法去当个主管或什么之类的。但是如果今天是晚5年，又太老了，又快要50岁，又太老了，所以也不适合转换跑道。那现在这个时间点，就再不转就来不及的这种感觉。那所以想说，好吧，那就来，正刚好这个机会就来试试看。待很久，12年出4圈，现在过得还蛮开心的。那感谢这个系啦哈，那还有这个学校，那就想说看看以后会怎么样。那搞不好以后会遇到各位哦，应该吧？毕竟我们学生有60%以上的人都去那里这样。OK，好，那11点了10分钟后见。I will see you after 10 minutes. Thank you. 对对对对，对不起对不起。啊，哇，好累哦。啊，当学生真好。其实我有时候在想啊，我小时候，我小时候在当学生的时候，怎么怎么这样子，怎么这样子上课跟念书啊？这样子可以吗？现在想起来了哈，以前小时候就是乱念，然后也没有，就是怎么讲，虽然有花时间，可是好像没有很没有很正确的在获取知识，这样我也不知道为什么。那当然还是有过考试啦，哈，就都有过，但是就是现在想一想，就觉得说以前做事怎么可以这样子呢？大概是这样的。那当然好，这样表示说好像是有成长嘛，对不对哈？那所以很有趣的就是说，那时候念这些东西，我会觉得超级难，然后我都觉得不可能会有一天会懂这样。但是到了老了以后，去去重新学一遍，然后我就觉得，哎，我为什么那时候不会？就觉得还蛮奇怪的，就是可能是学习的方法已经建立一个系统啊，就是大家知道这学习就是这么一回事，这种感觉，那就呃，所以就这样拼凑起来，就好像就好像比以前还要会这些东西，但实际上，对，就是哦，然后另外一件事情就是，我觉得现在的学生都比我那时候还要厉害，真的真的，就是我觉得我现在的专题生啊，哈，或是硕士生，我都觉得我以前在专题生、硕士生的时候，我都不知道我自己在干嘛。然后，但是我觉得现在的专题生跟硕士生在交大，尤其是在交大，然后我觉得哇，就是大家都非常非常优秀，呃，所以我觉得，哎，果然还是越来越厉害了哈。就好像是我好像觉得大家的平均身高每一代都会越来越高，就好像每个智力就越来越高这样。好，OK, so next let's continue our lecture. Now we enter to other different topic, okay, called mean free path and collision frequency. All right, so let's talk about collision when the particle traveling in the container. All right, so this is the particle blue. Blue one want to uh, hit others because this is collision, right? So imagine that if this particle touch others and it will go away. All right. So if it go here, it will go away. Particle go away, go away. All right. So we assume that it just go straightly. All right. So within time t, so within time t, the average velocity it will move in this distance v bar t, right? And the particle it hits is actually with all those particle center lie inside the cylinder. All right, all these particle centers align, I mean, inside this cylinder, and it will be hit. All right. For example, if this particle, its particle center is outside of the cylinder, it will miss, right? Because when it moves, they won't hit it. Okay. This blue particle won't hit this particle with the center outside of the cylinder. So now, if this particle travel at a time t with a distance v bar t, the number of particles it hits is the number of molecules per unit volume. All right. And this is volume of the cylinder. Okay? It is a cylinder. So where is the cylinder volume come from? All right. So this is 2R squared. What does that mean? 2R is this is R. Here is R. So 2R. 2R make a circle and times the height of the cylinder, V bar T. Okay, so this is pi 2R squared, the area. Okay, so N divided by V is number of molecules per unit volume, right? So now this is the number of the particle heated in the volume by the blue one. Okay, so the mean free path, average mean is average mean free path estimate. Okay, it's estimate. Is that estimate? E is V bar T divided by the total collision times. Okay, so now you see it is V bar T, and this we can written down as N on the bar. All right, N on the bar. It's a number of molecules per unit volume, and this we call it sigma. Well, whatever. It's a number. It's a constant. Okay, so it should be N over 1 over N on the bar sigma. Okay, and however, this one is an estimate. It's not exactly correct, because the problem is that the target molecular, the gray one, they are all moving. They has their own speed, right? So the collision depends upon the average relative velocity, okay, of the random moving molecule. So because they are actually moving, so their movement should be considered relative, okay, relatively, not the absolute. You know, they stop here, and they just bump it. So this is not exactly correct. So that's why we say it is estimate, LE. Okay, so this is not correct. So what is the exact? Well, it's not the real meaning, real definition of the L. L should be N on the bar sigma with a factor, just like before. We need to find a factor to correct this. Okay? Now, interestingly, in our textbook, it said the factor is A over pi square root in the textbook. Okay? But in the on the internet or our common sense, it's written down like this. Okay? And this one is because relative velocity. Okay, So, which one is true? Well, personally, I prefer this one. Okay? But in textbook, it said this. I don't know why. Well, maybe we have different perspective from scientists. I don't know. But yeah, that's it. So, so if you use this, okay, if you use this, and your collision frequency will be your most probable uh, velocity divided by L. Okay, and then you can get the collision frequency within this. Well, but I will give you supporting information for this result, all right, in the next page. So don't worry. But for both definition, it's okay. The important part is the mean free path is actually proportional to 1 over n bar, no problem, right? And also 1 over p. Why? Because n on the bar is equal to n over v, right? And it also related to p over kt. So it's also proportional to 1 over p. Okay? But independent of t, well, we will explain this later, but we will use this quite often, all right? We will use L proportional to 1 over p later. 好，我们现在讲一个新的课题哈，叫做平均自由路径还有碰撞频率，反正就是碰撞的状态了哈。好，那这时候我们就看这个蓝色要怎么样去撞到别人。那它在时间 t 之间呢，它会跑 v bar 这么远，好，平均来说会跑 v bar 那么 v bar 的速度，然后乘上 t 这么远。那什么叫做碰撞到？就是它们之间有碰到，像这样子就是最极限的碰到了，就是两个行星距离正好是 r 跟 r 的时候是正好是碰到嘛，哈。好，那这个蓝色往前走，那会碰到谁呢？会碰到几颗呢？那一定是其他的灰色的球，它的行星要在这个跑的路径，跑的路径之内，它就会被撞到。所以如果今天它的行星如果在外面，它根本撞不到啊，所以说最远就是最极限就是这两个状态，所以就是2r 的这个状态。好，那2r 这个状态，那个管子呢的体积呢，就可以用派乘上2r 平方来算，然后乘上它的高 v bar t， 好，这是它的体积。那这个体积里面有多少颗呢？当然就是要看 n 除以 v 啦，哈，就是平均单位体积下会有几颗，乘上去以后就表示说这一个颗数，这个蓝色的在 t 时间之内会撞到几次，就这样。好，那几次？那如果是 mean free path 呢？就会是它的行走的长度除上它碰撞的个数。但是我这边写了一个是 estimate， 就是一个粗估的、大略估计的，表示不是正确的哈。它是大约这样算一算，就发现它是 L 大概会长这个样子的形式。但是这不是对的哦，因为它在移动，其他人也在移动啊。好，所以其他人在移动，他们之间的碰撞应该要用相对速度来处理，平均的相对速度来处理，所以这边是不对的，没有那么好，就是它这个只是粗估的，所以又跟以前一样，需要去乘上一个系数，让它矫正回来。那这个矫正回来要怎么矫正呢？很神奇的是，课本上跟我们说，它需要乘这个东西根号8除以派，8除以派根号这个东西来当做是矫正。可是网络上跟我们自己平常在看到的是根号2，那不好意思，我真的不知道为什么，我真的不知道为什么课本会这样写，可能是不同的学派吧。 那他如果用这样的方式去算它的 collision frequency，其实就是 Vn 除以 L，那就是得到这个答案哈。好，那不过没关系我们等一下会补充这个的教材是根号2，这根号2怎么来呢？是平均相对速度来的。好，那等一下我们就会补充。那最后这个其实比较重要了哈，就是我们来看这个是 L，就是它的平均自由路径是跟 E 除以 N bar 有关。那 N bar 又跟 N 除以 V 跟 P 除以 KT 相等，所以 L 其实是跟压力是成反比的是成反比的。那等一下我们就会用到这个黄色的内容。OK, next, this is a supporting data, supporting information, supporting information. All right. So we have two particle, two particle, and two particle. All right, and this is V1, this is V2. All right, and this is random molecular velocities. Okay, so their relative velocity. Oh, by the way, I have an arrow here. Actually, the arrow means vector. Okay, so actually this is very similar to this. All right. But it's too waste of time to write down the bold in my Apple Pencil. So I just write down the arrow. All right, represent that this is a vector. All right, so V relative as a value. This is a value. All right. V relative dot V relative and equal to V1 minus V2 dot V1 minus V2. All right. And if we expand it, V1 dot V1 minus 2V1 dot V2 plus V2 dot V2. All right, we'll just expand it. All right, and this is one single V relative. How about average relative velocity V relative, but with the bar on it. Hey, copy. Increase a little bit. Hey, and it become this and that with a bar on it. Okay, and interestingly, V1 dot V2 bar actually equal to 0. Why? Because random, they will cancel each other. V1 dot V2, V1 dot V2. So they just dot, and they can be any direction. Okay, and then you do, because they do all the direction possibility are all the same. So when they do the average, they will cancel each other out, become 0. So your V relative will be V1 squared, V2 squared. Both of them has bar. And it should be random average. Okay, so it should be half, 2 square root V bar. Okay, and of course, V1 equal to V2 equal to V bar. Yeah, as you can see, this is random average, V1, V2. Because they are in the same container, if you have bar, it will be exactly the same, right? Random average. So V1, V2 equals to V bar. So it becomes square root to V bar. So that's how we get the blue one, the factor. 好，我们现在再补充一个哈，就是为什么这是根号？那我从网络上看，教科书看都是根号2，但是不知道为什么课本写奇怪的数字。没关系，好，总之我就补充一下为什么是根号2呢？因为我们使用的是提供给大家参考哈，就2颗，一个是 V1，一个是 V2，那是向量哈，加了一个箭头。我不想要写出题啊，因为那个太累了。好，那 V1 减 V2 是它的相对速度。那相对速度呢？那我们就来看它的单自己的速度是，就是速度相对速度的值是多少？那我们就2个 dot 嘛，好，然后再开根号就可以了。好，那这时候我们就把它展开，我们就发现它是长这样子的行为。好，这是 V relative 的值。那我想要知道平均的 relative， 平均相对的速度是多少啊？所以我们就加一个平均，每个都平均，好，没有问题。那平均完以后，我们就会发现这个东西的平均其实会等于0哦，因为 V1 跟 V2 是都有可能嘛，对不对哈？它可能正的，也可能负的，它做dot，它都有可能，所有的方向都有可能。那既然所有的方向都可能，全部加上起来，再除以它的个数，平均起来都会抵消的，所以这边其实会等于0。那等于0以后就可以写成这样子了。那写成这样子后，我们就发现 V1 bar 跟 V2 bar 其实是同样的耶。为什么？因为它是同一个气体嘛。那同一个气体，第一个速度的平均跟第二个速度的平均啊，大家都一样啊，所以它应该是 V bar， 所以就变成根号2的 V bar。好，那就这样子。Next， 哦，好累哦，晕头转向。可是我很想要把剩27、28、29剩还有4页。我想要赶快把这个教完，这样我就可以不用上传2次第4章了，加油！好，那我们就来看看 mean free path 跟 probability function 几率函数有什么关系？那没关系，我们就先看看几率函数。那这边有点是引入新的东西，但是我应该要讲英文对不对哈 ？Okay, now we'll talk about mean free path and the probability function Px. Their relationship, we want to correlate them and find the format expression, mathematical expression for this. All right, so probability that collision will occur in dx. So we just give a assumption, alpha value times dx. So when you travel dx, the probability that you hit others is alpha. All right. Of course, if you have longer dx, you will have higher chance to make collision to others. So this is the first type of the formulation. We can also have second formulation. Probability that a molecule will travel x before a collision. Okay, so the px won't collide others, bump to others. chance is px. The x is of course it's travel distance. So this is the probability. So now if we sum it up together, probability that not hit any other molecular with the distance dx and x, what will it be? So as we say, dx, travel dx, the bumping probability is alpha dx. So not bump to others is 1 minus alpha dx. Okay, so this is small range, a small distance. Not bump to others probability. And px is the probability that a molecule will travel x before a collision. So it's not bumping, right? So it travel x and not bumping. So px. This is what basically just put these two together. All right. And now let's think about it. Think about that. Because px is also valid for other direction, for other length, other distance. So actually, the same length can also be represent px plus dx in x plus dx direction, distance. So basically, these two should be 业务推销 the same. All right. So Taylor series. Okay. So I can write down. I can write down like this. Px plus dx equal to px times 1 minus alpha dx. Okay, as you can see, this long distance without bumping to each other equal to you go px and then times 1.1 minus alpha dx. So they must be satisfied simultaneously. So you need to you need to multiply them like this. Okay, and then we can what we should do. Let me take a look. Px. Oh, okay. So here we use Taylor series like this. Okay, and of course f is p, right? A is x, h is dx. So we can apply this Taylor series, but don't worry. This is all higher order term. This is a higher order term. High order terms. So which means that your dx is very small, right? So your dx is small, and then you do the square and cubic, blah, 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 blah. It will be even smaller. So we can neglecting them. So here, px and px prime times h is this dx. All right, so that's how it came from. Okay, so if you can accept this, we can get dpx divided by dx equal to minus alpha px. And then, interestingly, if you find this, some function is doing integration, differentiation equal to something times itself. It is exponential, right? This is exponential. And also, because it is minus alpha, you can go to, I mean, if you have in this form, you do differentiation, that minus alpha will go to the front, right? That's it. So your px must be looks like this, a e minus alpha x. And you also notice that why we are using alpha now, because here is minus alpha, okay? Now, we also continue px equal to exponential minus alpha x. Why? Because this is an ODE. We can apply boundary condition. Okay, what is the boundary condition? If there's no travel x equal to 0, you will have 0 chance to bump to others. Okay, so P0 equal to 1. 1 means that you will 100% don't bump to others. Okay, so A equal to 1. So that's how we neglect A because no travel, no heat. So now we know the probability function is actually Px equal to exponential minus alpha x. OK， 好，我现在要讲这一样就是平均自由径跟几率的函式 Px， 这几率函式就是这个几率函式，你可以走多远，然后不要碰到别人的几率是多少？这样子。好，那这个 P 就等于是说，你走 X 啊，你不会碰到别人的几率是 Px。OK， 好，那这时候我们就再去作为另外一个东西，就是说我换另外一个方式讲，如果你今天走了 dx 的路径，然后你会遇到别人，会撞到别人的几率是阿法乘上 dx， 你也可以这样写嘛，哈，就是这个数，就是 dx 如果越长，你的阿法就会越大，dx 越长，你阿法乘 dx 当然越大，所以几率也会越高。好，那这时候我们就把它放在一起，这就是数学家的聪明的地方，它是 trick。他说，如果今天你走了 dx， 你不撞到别人的几率是1减阿法 dx， 啊，这个没有问题，走了这一段。接下来你走了 x 段，你不会撞到别人的几率是 px。OK， 好，这样子可以了，就是把它写下来，这是它的几率，就是这两个乘在一起，就是他走这么远的不撞到别人的几率。但你转念一想，px 本来就是一个走多远然后不撞到别人的几率，那我不直接把 x 加 dx 带进去也是可以啊，对不对哈？所以这两个其实是完全相等的几率，所以我们的 px 加 dx 会等于 px 乘上1减阿法 dx。前面这个东西就是我们可以用泰勒展开式去展开，把后面的太小微小项把它去除掉以后，就可以得到这个式子。这是算一算就移动一下，发现这个 P 这个函式啊，你对它做微分，反而是它自己啊，那不就是 exponential 吗？而且你又发现它的系数是负阿法，那也就是它上面的它上面的 exponential 上面的系数一定是负阿法。OK， 然后我们就可以写出这个式子。但是 A 是多少呢？我们可以借由代入边界条件来解出来。什么意思呢？如果今天的 x 等于0，表示说你没有任何的走路，你当然不可能撞到任何人，所以你不撞到别人的几率是100%，所以你的 A 就会等于1。好，我们就可以写出这样子的式子。All right, so because we are talking about not bumping to others, so we can say this is we can say survival rate. Survival rate is that you are not bumped to others. Okay, survival. And then we want to connect the thing like so we have px, we also have fx. We have px is a probability function. Okay, what is a probability function? It looks like this, right? And the other is probability density function. What is density function? Which means that you need to do the integration and then to get the to get the probability. All right. So we want to get the relationship between P and F. Okay. And the F also related to, we can correlate it to the, because this is a density, probability density function always can link to expected value. So if we have the expected value not bumping into others is the mean free path. All right. So we using expected value to get the mean free path. Expected value mathematic technique tool, we need to come up probability density function first. Okay, so now you know P and F relationship. So your F is actually the dp x over dx. Do the differentiation so you can get fx. And so we do that. Okay, and we do that, we find that, oh, alpha times exponential minus alpha x. Maybe you will ask why there's no minus sign in the front. Because probability density function always greater than 0. All right, so that's the reason why we're adding a absolute value here. So we can have no minus sign because probability density function always greater than 0. Okay, and then if we have the fx equal to this, our mean free path is actually the x bar, which means that the expected value for the x that not bump into others. Okay, so that's how we do the 0 to infinity velocity. Distance, and x is the distance times its own probability density function, and then we do the integration. We can have L equal to 1 over alpha. Okay, so luckily we have px equal to exponential minus xl. Okay, so our px is actually n and no. All right, so the initial number of particle in the molecular beam, and after the travel, if the travel with the, so you can see that the probability not bumping to others is exponential minus x over l. So you can see that if we draw the figure for the px, and x is x over l, which means that how many times that you travel the distance, how many times of the mean free path. So if you travel mean free path, okay, you only have 37% not bumping to others. Okay, and of course, if you not travel anything, you not bumping to others is 1, no problem. Okay, and then of course, if you travel longer and longer, your survival rate will become lower and lower. Okay, so that's the meaning. 好，现在要讲的就是存活的几率，存活的方程式。我们要讲存活，表示说你要去跟它，就是要怎么样存活呢？我们来看一下，就是我们刚刚讲存活就是不重要别人不重要别人。那我们的刚刚已经 px 已经写出来了 ，probability function 写出来了，它长这个样子。但是这时候我们还是不知道 alpha 是多少啊，但是我们可以知道它一定跟 mean free path 有关系，对不对？那我们要怎么样把 p 跟 mean free path 连在一起呢？ mean free path 其实你可以想成是说，我们预期期望值它走多远，它不会被撞到，平均嘛，期望值 mean free path。好，平均自由路径，所以呢，我们就要把 p 转换成 probability density function， 因为你的期望值是需要用积分得到的，用积分 probability density function 来得到。那时候之前不是速度都是这样子吗？好，所以说只是这边变成距离而已。好，那这边的我们的 p 是几率，那既然要把它变成几率密度函式的话，也就是说我们几率密度函式做了积分以后会回到几率 ，OK？ 所以这个几率跟几率密度函式已经可以连起来了。那几率密度函式又可以透过 expected 期望值的方式得到平均自由路径。好，所以 用这样子的方式就可以连接这三者。OK， 好，那我们的 fx 其实就是 p 的微分嘛，对不对？哈，那我们发现微分下来应该是会有一个负阿法在前面，可是不对啊，因为我们的 f 它是 probability density function， 它是几率密度函数，都会是正的，所以我们这边加一个绝对值，不会有负的 sign 啊，不会有负的符号。好，我们的 fx 就写出来了。我们的 fx 叫做几率密度函数，那我们只要乘上它的距离，然后从0积到无穷大，再乘上它的几率密度函数，就会是它的期望值咯。距离的期望值，不会撞到的距离的期望值啊，那不就是 mean free path 吗？好，所以我们的 L 会等于它的 x bar， 然后算出来积分结果是1除以阿尔法，所以我们终于找到了 ，OK， 阿尔法就是1除以 L。那这时候我们就可以把 px 完完整整的写出来了。那这个写出来以后，也就是说，这个撞不撞，就几率撞走 x 的距离不要撞到别人的几率，这件事情当然一定会跟你的 L 是有关系的嘛，对不对？好，你的平均自由路径是有关系的。好，那你就做出来这件事情以后，我们就可以画出一张图。如果你今天跑了 L 的距离，也就是你跑了平均自由路径的距离，你有多少的 percent 是不会撞到别人啊？你有37% 不会撞到别人，剩下的63% 你就撞到别人就飞走了。OK， 好，大概是这样。那如果你今天不跑的话，当然就不会撞到别人，100%不会撞到别人。好，所以这边是1。OK，next let's talk about effusion. Effusion is actually the gas through the small hole, and the equilibrium state of the gas still remain. Okay, still remain will not be affected. Okay, so which means that the hole is so small that even the leakage won't affect the equilibrium state of the container. All right. So the area of the hole with a diameter d pi d squared over 4. Okay, you can see that we can imagine that there's a small hole. Okay, the small hole on the container, and the hole is so small, like this. And what small is small? How small is small? Okay, so let's take a look. So d here is d squared divided by 4 times time. So this is the area of this hole, right? Okay. We see that how small is small. It is much less than 4 pi L squared. What does that mean? It means that if you have a particle here, their mean free path is L. Okay? If the mean free path is L, which means that if it travels to here, it typically will meet other particle and bump to somewhere else. So it won't escape. Mean, averagely, it will go to here and then bump to others. And then it won't go out of this hole. So the L is crucial, okay? The L, the range is that typically it won't go out within this region, okay? And if this area is much greater than this D, which means that, yeah, the D is small, the hole is small, okay? So this is a criteria that the hole is so small, okay? So if we can accept that, let's see, the D square is much less than 16 L squared. So let's interpret what is small, much smaller. If we say 100 times is small, so we will say D squared less 0.16 L squared. Okay? And then we found that, oh, D need to be less than 0.4 L, and then it can be say small. Okay, and then we found that L greater L, which means that it's easier for D. Okay, so we said the L is actually 1 over P. L is actually not proportional to counter reverse proportional to the P. All right, so which means that the P need to be small, so your L can be greater, and the greater L is easier for D. So effusion is essentially a low pressure phenomenon. If the pressure is high, no effusion requirement can be meted. All right, so this is L is proportional to 1 over P at page 25, right? So now for ideal gas, we can write it down. How can we hit that area? Sorry, I cannot finish that within 2 minutes. So sorry, next time we still have a little bit 2-page PDF for PDF 4, right? Sorry 我就说我没办法讲完 PDF 4，我原本想要讲完的，在想说这次就可以直接 upload PDF 4一次就好，但没想到我还要再讲2次，然后就再下次还要再讲2页太可惜了，好吧？不过我也没有精力了，那我们就下次再继续上吧。那我要不要快速讲一下我刚刚的翻译哈？就是 effusion 它其实就是一个东西一个 container 一个容器有小孔，那个小孔太小了，所以东西 leak 出去漏出去，它也不会影响到它的平衡状态。那什么样叫做小呢？我们就发现，如果今天有一个洞，它的直径是 d， 那它要怎么样叫做小？也就是它不容易被飞出去嘛，也就是说这个 particle 不容易被飞出去，它表示说它在这个平均自由路径的这个路径的状况这个范围里面，它如果跑到那边去，它很容易平均出来，它会被撞走啊，对不对它就出不去了。所以这样子的大小来去比较它是刚刚好的。那也就是说，如果今天这个 d 很小，那怎么样才叫小？就是这个范围对它来说是很大的话，那就表示它就叫小。所以我们的这个孔的面积要远小于这个灰色球的面积，这样就叫做小。好，那我们就算一算，发现，如果把这个小于100倍叫做远小于的话，我们就发现我们的 d 要小于 0.4L 才叫做小。那这时候我们就发现，其实 L D 要小于 0.4L 其实很难的一件事情那L 的话是平均自由路径，平均自由路径需要如果 L 越大，就表示这个洞人类越容易造出来越容易造出来。那所以 L 其实是跟 P 是成反比的。所以说，如果今天要提高 L， 我们就要在低压下才会让 L 提升。低压下 L 提升的话，我们才比较容易制造出那个洞，才容易制造出这个现象。所以实际上 effusion 是一个低压的现象。好，那我们今天就上到这里。Thank you, and I will see you next week. 是，来啊，我要走了。